A few calculations with Pascal's principle and gauges for your viewing pleasure. First of all, let's go back to that enormous column of water picture here. So we already saw that with a mercury barometer, the maximum height would be 76 centimeters or 760 millimeters. We didn't derive that, I just told it to you. But now let's look at how we can derive that, and let's do it for water first. So we've got column of water, and how high can that be with 1 atmosphere of pressure? Well, if I think about the pressure is 0 here at the top and 1 atmosphere at the bottom, well, I can just use P equals rho GH. That's kind of laggy, I'm not sure why. Anyway, and that pressure at the bottom is under a height of h, so we can just plug in what we know, 1 atmosphere for pressure, which is 1.013 times 10 to the 5th newtons per square meter. Then we're going to plug in the density of water times 9.8, and then solve this guy for h. Easy enough, we're just going to divide those to the other side. Turns out that we get not 76 centimeters, but 10.3 meters high, so 30 feet high. Nice big giant column of water. Now if we have something even less dense, gasoline is less dense than water, that's why it floats on top. We're going to have the same calculation, 1.013 times 10 to the 5th, and instead of having 1,000, we're going to have 680 times 9.8 times the height, and in this case we get a whopping height of 15.2 meters. So the point is, the less dense the fluid, the higher the column is going to be, because you're dividing by a smaller number. Now for mercury, the density of mercury is quite high. It is 13,600 kilograms per cubic meter. And so when you plug that in, that's when you get 0.76 meters. So using a dense fluid makes for an easier design of a barometer where it can be less than a meter high. Alright, next one. Let's say we have a curved tube like this, and first we put water in, and when there's just water in, both ends of the tube, both columns, the water is going to be at the exact same height. Oops. Anyway, if it's up to here on that side, it's going to be at the exact same level on the other side. And now if we add oil to the top, then it's going to make things a little bit more complicated. That oil is going to push the water down here, which is going to cause it to go up here a bit, but the weight of the oil is less than the weight of the water, and so we're not going to have the same level anymore. But what we do know is this line here, A and B, that has to be at exactly the same pressure, because if you think of the pressure down here at the bottom, whatever it is, and you come up, the pressure is going to decrease, decrease, decrease. Well, if we start at the same pressure down here and come up the exact same amount, it's going to decrease by the exact same amount. So as long as we're still comparing water to water, any equal height of water on the bottom here has to be at the same pressure. Okay, so what that means is now we can just call this bottom part 0 or whatever, and we just need to think about the weight of the fluid on top. So the weight of this fluid here has to equal the weight of this fluid here, and that's one way you could get at this problem. We want to find the density of that oil. But since we're doing pressures, we could, and we know that the pressure right here is equal to the pressure right here, we can say that the pressure at location A equals the pressure at location B. And then if we plug in rho GH for each of these pressures, now in this case the depth in the fluid on one side is oil and on the other side is water. So at location A we have the density of the oil times G times the height of the oil. And on the other side, we've got the density of water times G times the height of the water. We can get rid of the G's, those are the same on both sides. And density of oil is what we're going to try to solve for, so that's our unknown. The height of the oil is given, so 0.48. Density of water is 1,000, and the height of the water is 0.36. So we just divide 0.48 to the other side, and we get density of oil. And we should be expecting something less than 1,000 because we said the oil is less dense, otherwise it would be lower if it were more dense. This works out to be a nice round number of 750 kilograms per cubic meter. Okay. And just to show you a little bit more about what I mean by having the pressures the same at that level, here's a little applet from that same FET website. If you look up the fluid pressure and flow applet, now I've put these pressure gauges here ahead of time. So these two are at the exact same level, and these two are at the exact same level. And it doesn't matter what's going on above or below or what shapes of walls we have. We can change the level of our water, and as long as you're at the exact same height from the bottom, these pressures are always going to be equal, as well as these pressures. We've got a drain here on the bottom as well, so if we go too far, then there's no pressure in the water, right? Oh, then it's atmospheric pressure. Okay, so that's what I'm saying, where locations A and B, despite what's on top of it, those two locations, as long as it's water all the way through, those have to be the same pressure. Alright, one more thing to look at. We have a pipe running down a 42-meter high hill. So we've got some hill here. It's a 25-degree angle, so kind of a long hill like this. And we're given this over here is 42 meters. This here is my angle. And I want to know the pressure at the bottom of the pipe. So I've got some pipe here running along the hill. And by pressure we mean gauge pressure. So let's say that it's capped off and the pipe is not, the water's not running out. This side of the pipe, if it's open, is going to be at atmospheric pressure. So the nice thing about this is we don't have to worry about that angle at all. Pressure is still rho GH, and that H, all that matters is the vertical height. This kind of harkens back to when we studied energy, and we said the angle of the hill doesn't matter if I have a ball rolling down a ramp. All that matters is the height. At the bottom of the ramp, it will have the same speed regardless of the angle of the ramp. Now, it will get there faster with a steeper ramp, so it would be a big acceleration for a short amount of time with a steep ramp, smaller acceleration for a longer amount of time for the larger ramp, but the speed doesn't matter. Same thing here with pressure. The angle of the ramp doesn't matter. All that matters is my vertical change. So all I have to do is plug in nice and easy to this equation here, and I will get 411,600 newtons per meter squared is the gauge pressure at the bottom of that pipe. Now the next question here, if it had a vertical opening, so this pipe kind of curved up, something like that, and the water comes shooting out, yay, water shooting out, how high will that water go? Well, just like I said with energy of the ball, if it rolls down and if it rolled back up, it would go just as high because of conservation of energy. Same thing with this water. We're ignoring any internal resistance of the water, what we call viscosity. So if the water goes down and shoots straight up, it will go just as high as it started. So we'll go back up to 42 meters, and let's jump over to our applet again. So here I've got a somewhat similar situation. I've got a water tower, the pipe goes down. Even if it goes down like this and comes back up, I'm going to open this door here and we're going to have water come shooting out here. Okay. Oh, I'm going to keep my tank full. Here we go, match leakage, that should help. Alright, so eventually when this settles out, now you might have noticed it was higher for a little bit. The reason why it was higher was that was the water that was originally up at the top of the tank coming back up to its original height. But now when we have this kind of steady state situation here, where this water here is coming out and coming up to the exact same height, if we turn this off, let the water go down a bit, then this should drop a bit. Let's turn it back on. And eventually we are going to stabilize again at this height. Alright, that is all.